This is a sample called StateChange, in which we spawn a field of cubes, and we have this circle within which we color all the cubes red and spin them around their y-axis, while all the cubes outside the circle are colored white and don't spin. When the user clicks on the field, they can move around this circle, thereby toggling cubes between these two states. The key thing about this sample is it demonstrates 3 different ways to handle this state change. In the first approach, the cubes have a spin component with a Boolean flag that we simply toggle true and false. In the second approach, we add the spin component only to the cubes inside the circle and remove it from those outside the circle. And in the third approach, we disable the spin component on the cubes outside the circle. So looking at the scene, we have a subscene that contains this config where we specify the prefab for our cube, the number of cubes in each row and column, the radius of the circle, and one of the 3 modes I just described, using a value, using structural changes, meaning adding and removing components, or using an enableable component. So in the Baker of the config authoring, for each field of the config authoring model behavior, we plug its corresponding value into this config iComponent data. And then we also add this hit component, which stores a float3, the position where we click on the field, and a Boolean flag to signal if the hit has changed this frame. We also define here an enum specifying the mode, and the spin component, which contains a Boolean and also implements enableable component, meaning that the spin components of entities can be disabled. In the input system, the onCreate method specifies that the system should not update until hit and config both exists when they are loaded from the scene. And then onUpdate notice is not marked with the burstCompile attribute because this method accesses the camera, which is a managed object, and so the method can't be burstCompiled. First thing in the method, we get the hit and set the hit change to false. And then if for whatever reason there is no camera or the user of this frame has not clicked the main mouse button, then we just early return. Otherwise, if there is a camera and the user has clicked, then from the mouse position, we create a ray shot from the camera into the world and do a raycast to see where that intersects with the XZ plane. If it does intersect, then we set hit change to true and set the value of the hit to the ray's point of contact. In the CubeSpawn system, we access the config singleton. That's why we have a require for update on config. And because we want to respawn all the cubes when the user modifies config authoring in the editor, we have this config field in the system to cache the prior config value, and if that matches the current config value, then the config hasn't changed and we just return. Otherwise, we update the prior config to be the new config for the sake of the next frame. We destroy all the existing cubes, if any exist, and then we instantiate the cube prefab, creating the config size squared number of instances. We then use a for each query to set the local transforms of all the cubes, positioning them all in their appropriate position in the grid. And then, depending upon the selected mode, we need to modify the cubes. For the structural change mode, we don't need to do anything, but for both the value mode and the enableable component mode, we need to add the spin component to all the cubes. And for the enableable component case, we need to disable the spin component of all the cubes. Small side note, this requires us to create this second query we call spin query, even though it will actually match all of the same entities as this first query. The reason we can't just use the first query in this call is that it doesn't specify that all the entities have the spin component, and so we can't pass that query to a set component enabled call for type spin. In the spin system, depending upon the mode, we're scheduling one of 2 jobs. For the value case, we schedule this spin by value job, and for the other 2 cases, we schedule spin job. In both cases, we set the job offset field to be the rotation around the y-axis that we're going to apply to the spinning cubes. The spin by value job is an iJob entity, which matches all entities having a local transform component and spin component. And in the execute, it simply checks the Boolean of the spin component, and if it's true, we rotate the transform by the offset. The spin job for the other 2 cases is even simpler. It processes all entities having a local transform and the spin component, but in this case, we don't need to actually read the spin component. In the structural change mode, only the cubes we want to spin will have this spin component, and in the enableable component mode, all cubes have the spin component, but only the cubes within the circle will have it enabled. So this job will only rotate the transforms of the cubes inside the circle. Now, note back up in the update, for profiling purposes, we're getting a timestamp before we schedule the job, and then we get a timestamp after we schedule the job, and then we compute the elapsed time and feed that to a custom profile module, as we'll see when we look at profiles. The set state system is the system that toggles the cubes between their two states. It first checks whether the hit has changed, and if not, it'll just early return because there's nothing to do. But otherwise, it'll go on to schedule jobs that set the state of the cubes. In the value mode case, it schedules this set value job, and this job is an iJob entity that matches all entities having a local transform, a spin, and URP material property base color, which is the component we set to modify the color of the cubes. In the execute, we simply do a distance check, and if the cube is within inside the radius of the circle, then we set its color to red and set its isSpinning value to true. Otherwise, we set its color to white and set its isSpinning value to false. For the structural change case, we have an add spin job and remove spin job. The add spin job processes all entities having the local transform component and the URP material property base color component, but which don't have the spin component. Those are the entities to which we need to possibly add the spin component, and we do a distance check to see if the cube is inside the radius. If so, we set its color to red, and through an entity command buffer, we add the spin component. The remove spin job looks the same, except it only processes entities which already have the spin component, and in the case where the entity is not inside the radius, it sets the color to white and removes the spin component. So once these two jobs are done and their entity command buffers are played back, all the cubes within the circle will have the spin component, and all the cubes outside the circle will not. Lastly, for the enableable component mode, we again have two jobs, enable spin job and disable spin job. The enable spin job is actually exactly like the add spin job, except in this mode, all the cubes always have the spin component. It's never removed. For the cubes within the radius of the circle, instead of adding the spin component, we simply set its enabled state to true. In the disable spin job, we end up not needing an entity command buffer because through this enabled ref of the spin type, we can actually just set the enabled state to false directly. But understand that by including this enabled ref RW of spin as a parameter, the query only matches entities that have an enabled spin component. So unfortunately, we can't use this same type of parameter in the enable spin job because that job needs to process all the entities which have spin disabled. And unfortunately, a job that uses this attribute can't also include the enabled ref RW. Admittedly, there's actually really no great reason for this limitation. It's actually just an oversight in the current API. So that's why in the enable spin job, we have to use the entity command buffer as a workaround. So let's look now at how these different modes perform. First, the value mode. I'll let it run for a bit, and then I'll click and move around and let go. And as you can see, the cost of the spin system by itself is about 1/5 of a millisecond. But then when we hold the mouse down, we're paying the cost of setting the state, and that's taking about 2.7 milliseconds, which is a quite significant cost, but understand that we have this configured currently to have 1,000 by 1,000 cubes, so 1 million cubes. And remember that in the value mode, setting the state requires looping over a few components of all of the cube entities. So the cost for the spin system and set state system should not be too surprising. But when we look at the frames, even frames where we're not setting the state at all, the overall frame time is surprisingly high. The main part of the player loop is taking over 20 milliseconds, and you can see that most of that is taken up by presentation, by rendering. And if we look at the worker threads, we can see what's happening. Certain transform-related and then rendering-related jobs are taking up quite a bit of time. The problem is that the job scheduled in the spin system accesses the transforms of all 1 million cubes, and because it does so with write access, that marks all of the cubes in their chunks as needing processing by the transform system. So we're paying a lot of transform and rendering overhead here for cubes that aren't actually changing in the frame. Relative to the whole field, the circle is relatively small, and so most of the cubes are not currently active, yet we're paying a significant overhead cost even for the cubes that aren't currently spinning. In the structural change mode, here I'll click and move the mouse around a bit and let it settle. Well, we see some interesting things here. only when we place a circle do we start seeing a cost for the spin system, because only now do some entities have the spin component. The set state system cost is also cheaper by about a millisecond, and this difference is harder to account for. The only obvious savings in this mode is that we're no longer reading and modifying the value of the spin component itself, so there may be some memory bandwidth savings there. It may be incurring fewer branch mispredictions because the spinning cubes and the non-spinning cubes are grouped into separate chunks, but I'd have to do deeper profiling to verify if that's the case. Keep in mind that this reported number does not include the cost of playing back the entity command buffers. If we look up here in the player loop, we'll see under the simulation system group, we have this begin simulation entity command buffer system. That's over 5 milliseconds, and that's where we're paying the actual cost of adding and removing the spin component. So the time running the jobs may have gotten faster, but the total real cost in this mode is significantly higher. Lastly, the enableable component mode. I'll click and move the mouse around for a little bit, let go. What you see is that while now, unlike the structural change option, we are paying some cost in the spin system even before we have any spin-in cubes, and that's because in this mode, all of the entities always have the spin component, just for some of them it may be disabled. And so the job in the spin system, its query has to check each chunk to see if they have any enabled spin components. The set state system, though, has basically the exact same cost as in the structural change mode, and that's because in both modes, the set state systems do have to visit every single cube, and the work involved is virtually the same. However, now, if we zoom in and find the begin simulation entity command buffer system, we'll see it's far, far cheaper. It's taking less than 1/5 of a millisecond here, compared to the over 5.5 milliseconds in the structural change mode. And this is because it's far, far cheaper to simply set the enabled state of a component than to add or remove a component. Adding or removing a component requires moving the entity to a different chunk, but setting the enabled state of an entity basically just flips a bit. So we might conclude from these results that the value mode is the worst option, structural changes is an improvement, but the enable component option is the best of all. And that is a valid conclusion when solving this specific problem at this scale. However, imagine we want to implement the sample, but the target scale is much, much smaller. Well, maybe then the performance differences are much less significant. And depending on how frequently we expect to change the state of the cubes, well, under some circumstances, maybe it's worth paying the cost of the add and remove component structural changes, because then we get the fastest possible queries. And consider other scenarios where you need more than 2 discrete states. Here, for example, say we have characters with many different states. Well, rather than representing those state changes by adding and removing components or enabling and disabling components, simply storing an enum value in a single component is usually both simpler and actually often the most performant. It's true that we can't query entities by value, but typically in this scenario, your core logic is a state machine that needs to handle all possible states. So as long as you're going to be processing each entity once per frame regardless of its state, there's not too much lost handling them all in one big query. This approach does probably incur some extra branch mispredictions, but on the whole, particularly for the scale of most real-world problems, that cost is generally outweighed by the benefits compared to the alternatives. There is, though, one thing to watch out for in this pattern, and that is the case where different states, different branches of the switch here, need to access a lot of different data. Like here, perhaps in the idle state, we don't need to access any data, but then say in the other states, maybe we need to access a bunch of transform and animation data. And then in the worst case, maybe there's a state where the character does their taxes, and that requires accessing many, many pieces of data, some of which perhaps is stored of components on the same entity, and so we can just add them to the query, but in other cases maybe is totally separate data. The problem then is that if for the sake of this one case, we have to add additional components into the query, then we are paying some access cost for all of the entities in the query, not just the ones doing their taxes. Probably more worrisome, it means that the system in which we run this for each, or perhaps a job that we put this code into, those systems and those jobs then would be greatly expanding the scope of data that they access, and that has implications for job scheduling. If just for the sake of handling taxes, this code has to access 10 different components, the job or system containing this code then has a conflict with all the other jobs and systems that might access any of those same components. And that means that some jobs which may otherwise have been able to run concurrently with each other now have to depend upon each other and run in sequence. Any job or any system that is accessing many disparate parts of data may represent lost opportunities for concurrency, meaning suboptimal core utilization. So a solution here then is that for the character entities in this particular character state, we can in some way just defer the work to be processed later. Like imagine we have some queue to which we append the entities, and then some system or some job later will do the taxes for all the entities in that queue. This is not a totally ideal solution because it does imply we'll have to do random lookups for all the entities in the queue, but unless there are thousands of entities needing to do their taxes each frame, that cost is probably not very significant.